I'm Atef Hamada from University of Olo. Today we will talk about enhancement of mechanical properties of high manganese tube steel with flash heating process. This new technique for thermal processing of steel.
You present.
Okay, that introduction about flash heating technique. Okay, now for if you have control to grain structure, you make like heavy cold rolling or hot cold deformation, and they make annealing. But sometimes we have two types of annealing: the conventional annealing with heating rate like very less than 20 Kelvin per second. But now we have new technique called flash heating processing technology. This will make like fast heating rate with almost heating rate more than 500 centigrade per second, or sometimes can lead to 1000 centigrade per second to like suppress recrystallization, and you can control the recrystallization process. Okay, this systematic drawing to show the comparison between conventional heating process and flash annealing. For this cycle A, you can see here very fast heating rate can reach 1000 centigrade per second, and holding it can be like 1 second or without holding, and then fast cooling. Also, like cooling rate can be also reach 500 or 1000 centigrade per second. And this now without time or like very slow, very fast. This is for flash. But for conventional heating process, this now is applied in industry. You can see heating rate less than 20 centigrade per second, and we have like long time heating, and cooling can be slow cooling also. But you can see difference in time, different in holding time. Okay, now the study of our the aim of our work just to like to control the grain structure of austenitic high manganese tube steel through the concept of flash and heating. The experimental work. Okay. In this work, we have employed the Global simulator, but now I will show you also we have different line in our university in Olo. So now we have you apply this is the cast material to be steel, and of course we apply homogenization at 1200 for 4 hours and make the roughening and hot rolling, and then we have applied heavy cold roll about 80%, and then here we have applied flash annealing at different temperature. For example, we make fast heating with 500 centigrade per second, and make holding at 1000 for 5 seconds, 1100 for 5 seconds, 1200 for 5 seconds. But in the same time, at 1200 centigrade, we make without holding, just reaching 1200 and fast cooling, and then 1 second at 1200 and fast cooling. But here we about 5 seconds, 5 seconds, 5 seconds, but 1200. So now we have 5 different conditions, and cooling rate is like 400 centigrade per second. And this one applied using Global simulator. Okay. But this we have now Global simulator normally use very short sample, very small sample. But this line we have this new design in using also flash annealing processing using high frequency induction. So this is our sample. It can be used like 10 meter sample. Dimension of the sample, very long sample, 10 meter, and the width can be like 100 millimeter. But this new sample, but we don't apply this one. We don't apply this in this work. But just in our, just I show you, we have now different machine like Global for flash annealing, but this one we have high frequency for a long sample, and this you can use this our sample can be like 10 millimeter, and width can be 100, and this is a coil, and here barometer to measure the temperature here. This for semi-industry. Okay, this is the line specification, like the sample description. We have used like power sources about 15 kilowatt, with 4 is the total power capacity about 60 kilowatt. So we can, using this line, we can use heating, apply heating rate 1000 centigrade per second. But for Global, normal we use like 200, 500 maximum. But this this line we can use like maximum, we can use like 1000 centigrade per second. Okay, so this chemical composition of tube steel, 0.6 carbon and 22% manganese. Of course, we have used like heavy cold roll, 80% cold reduction, and then after that we applied microstructure characterization using electromagnetic scattering diffraction and tensile. Of course, for mechanical, we want to see the tensile behavior of the structure. Okay, this is the result. This is the thermal cycle we applied using Glibel. For example, you can see here. Okay, this recorded by Glibel. You can see here. Okay. For after that, from here to here, like we calculated almost the time from room temperature to 1200. It like take it like 2 or 3 seconds. It means the heating rate almost between 450 to 550. And you can see without holding and quenching, fast cooling, and also 1 second, 1200. But this 1000, 1100, 5 seconds, and 1200, 5 seconds, and then fast cooling. Okay, this is a green structure after 1,005 seconds. You can see here we have like polyrecrystallized structure with fine green. But okay, now we'll show the difference between and after. Okay, at this 1,000, and you can see at 1100, you can see the green structure now is coursing, but fully recrystallization. And at elite, of course, 1200 will be the same, but more coarsening. Okay, come to the now green side distribution, and we calculated for 1000. We found the green side structure of almost green African green side 2.5 Fourier crystallization, and at 1100 almost 10 microns. At 1200 with me 23 microns. Okay, this is a flash annealing Fourier crystallization and green side equiaxis and but coarsening at 1200. Now we come to the 1200, but without holding 1 second and 5 seconds. We can see here without holding, just 1200 flash annealing and cooling, fast cooling, and give also fully recrystallization. But something it was like very strange for us. We have the structure, it was like coarse green structure. And the same for 1 second, there is no difference between 1 second and 0 second without holding. But here, of course, even at 5 seconds, the difference it was very slight. Here at 1200 without holding, 0 second gives the green side 21 micron. There is no difference with after 1 second, the same 21 micron. But even after 5 seconds at 1200, the green structure, it was like 23 micron. So there's no difference. The difference comes from the temperature, but not dependent on time. Here's the green size with the temperature flash annealing. You can see here the green size here, and this is the flash annealing 1200, 0 second, 1 second, 5 seconds. But here, 5. Okay. This one, we have this old data for our work, 700 for 30 seconds. Also flash annealing, fast cooling, fast heating at 700, and then holding for 30 seconds. You can see here, green side 21, 21, 23. So, but only at 1200. So the difference in green side is very slight, but here with temperature different 1100, 1000, you can see the green side slightly sharply decreased. Now come to the mechanical properties. We can see here, okay, because we want like to make fair comparison. We select the different temperature, but for the same time. You can see here, okay, the 1000 because the green side almost like 2.5 give like higher yield strength with higher tensile and still elongation almost. And this some we have like extreme elongation more than 100% elongation. But here we can see at 1100, 1000, still something, there is comparative in mechanical behavior. However, at 1200 for 0 second, 1 second, 5 seconds, still the mechanical the tensile behavior for the 3 sample almost comparative, like there is no big difference between them. Because the green side here was like similar, almost 21, 21, and here 23. So that's why we didn't find any like significant difference in the mechanical behavior between the material flash annealed at 1200. Okay, this is just comparison. Okay, to be hurry, I understand.
Yes.
But okay, the most important, okay, you can see here, so go back. Sorry, back. Okay, this for 700, you can see 700 for 30 seconds. We can see that tensile strength much higher and also yield strength about 500. But okay, ductility is still, okay, it is, we can see still high, about 60% comparison to the carbon steel. So now we make some good comparison for other steel. Yeah, this interesting map. Okay, now we see like multiply tensile strength with the total elongation and yield strength. Okay, for this all carbon for tube steel from reference, we can see normal industry we like to multiply UTS tensile strength should be like 40,000 40K should be like this is our reference for this. But our result gives us more, almost can start like 80K, so much higher than other 2B steel. But because this steel uses like conventional heating, like long time, so that's why our present work gives us much better than other material. And also this one 700 for 70. For 30 seconds give us also good result. You can see more than 60, but this our reference, this for industry. So now this material to be steel including niobium, and this also here you can see from this one. So anyway, so we suggest if we have like this without any microalloying element, vanadium or niobium. So if you add niobium like this or vanadium, it can be like yield strength be like shift, would be like very high, would be like here. So it can be like much better than other material. So this technique is promising for processing, steel processing in industry. Okay, we applied physical based model. Bed is the key component like dislocation density, dislocation mean free path, and back stress. And this is the result. Okay, you can summon if you need it. We can see here like dislocation density at 1000, of course, will much higher than the other material, and also for back stress, also for 1000 higher than other material. So this is a physical modeling for the tensile behavior. Okay, conclusion. Okay, now it's applied this technique will give us fully recrystallization of cold rolling. Although, okay, in carbon steel and other material, normal we applied flash annealing to enhance or promote partially crystallized material. But because the recrystallization kinetics of tube steel very high, so we can get fully recrystallization material without holding time, but just depend on the temperature. Even, okay. We have get like tensile mechanical behavior is much higher than more high ductility, almost all the steel more than 100%, and in material at 1200 we got like ductility almost like 120%, 120. So this my presentation, and thank you, Titus and Dennis.